In this video, I'm going to talk about magnetic force. Force is F, B is for magnetic field, so FB is magnetic force. Let's say we have a charged particle, a positively charged particle, and I have two magnets. So the north pole of this magnet, this is the south pole of this magnet, so there is a magnetic field pointing from north to south. When this charged particle is moving through this magnetic field, it would experience a force. We call it magnetic force, FB. How do we write an equation for this magnetic force? FB equals, so we got a charged particle, a charge, Q. And this charged particle is moving through a magnetic field, B. So FB equals QVB, so sine theta. Theta is the angle between velocity and magnetic field. If theta equals 0 or theta equals 180 degrees, then sine theta equals 0. Force will be 0. Yes, this is our equation for magnetic force, FB equals QVB sine theta. So if you have a charged particle that is moving through a magnetic field at an angle theta, where theta is the angle between velocity and magnetic field, the equation for magnetic force is QVB sine theta. Maximum magnetic force is when theta equals 90 degrees, sine 90 equals 1, FB equals QVB sine 90, that is QVB. QVB is the maximum magnetic force. So if a charged particle is moving perpendicular to the magnetic field, just like this, the velocity vector is perpendicular to the magnetic field vector. This is the velocity vector, and magnetic field vector is from north to south, upwards, P. The angle between them is 90 degrees, and this particle would experience maximum magnetic force. The magnitude of that magnetic force would be QVB. Now, minimum magnetic force is when theta equals 0 degrees or theta equals 180 degrees. In both these cases, sine theta would be 0. Sine 0 equals 0. Sine 180 is also equal to 0. FB equals QVB times 0 is 0. No magnetic force. If there is magnetic field in this direction from left to right, let's say uniform magnetic field B, and this is my charged particle, it is moving to the right parallel to the magnetic field, just like this. The angle between the velocity vector and magnetic field vector is 0. This is the direction of velocity vector, and magnetic field vector is towards right. Theta equals 0 degrees, magnetic force would be 0. So this particle wouldn't experience a magnetic force, but that's not the case here. The particle is entering the magnetic field at an angle 90 degrees. So this charged particle would experience maximum magnetic force, and as a result, the shape of the path wouldn't be a straight line. It would deviate from that straight line path. So let's talk in detail about the shape of the path of a charged particle moving through a magnetic field. I have a positive charge here. In the first case, the particle is moving parallel to the magnetic field in a straight line. The velocity is on x-axis, v. It has only x component, vx. There is no y component, vy equals 0. Angle between velocity vector and the magnetic field vector is 0 degrees. Theta equals 0 degrees, sine 0 is 0. FB equals QVB sine 0, which is 0. There is no magnetic force. So this particle would continue moving in a straight line. In the second case, my charged particle is moving perpendicular to the magnetic field. It's entering perpendicular to the magnetic field. So its velocity vector is pointing up. This is the direction of velocity vector. It has only y component, there is no x component. The angle between velocity vector and magnetic field vector is 90 degrees. Theta equals 90 degrees. Fb equals qvb sine 90. Sine 90 is 1. Fb equals qvb. It would experience maximum force. As a result, this charged particle would move in a circular path through this magnetic field. In the third case, this charged particle is entering the magnetic field at an angle theta. Its velocity vector is in this direction, v. This velocity has x component vx and y component vy. The magnetic force is due to the y component of the velocity. So the particle would try to move in a circular path. This is due to the y component, but the x component would push it forward. So the shape of the path would be helical, just like this. Y component of velocity is responsible for the circular motion, and x component is responsible for the linear motion. The circular motion plus linear motion would result in a helical path. This particle would move in a helical path. Let's derive an equation for the orbital radius of the circular path. I got a charged particle, and this charged particle is entering the magnetic field at an angle 90 degrees. It would experience a magnetic force. This magnetic force provides the centripetal force that would keep the particle moving in a circular path. So we can write magnetic force is equal to centripetal force. And what's the equation for centripetal force? F equals ma. So centripetal force equals m times centripetal acceleration. Centripetal acceleration is v squared by r, so m times v squared by r. That's the equation for centripetal force. And for magnetic force, we already have the equation qvb sine theta. Theta is 90 degrees, so it's just qvb. Replacing fb with qvb, qvb equals mv square over r. qvb equals mv times v over r. We can cancel out this v and this v. The equation is now qb equals mv over r, and we need an equation for orbital radius r. So r equals mv over qb. Mass times velocity is momentum, so it's p over qb. That's another equation for orbital radius r. If a particle is entering at an angle theta, then this v should be the y component, vy over qb. Solve a problem. A proton enters a 0.65 Tesla uniform magnetic field at an angle of 30 degrees related to the magnetic field lines. What is the radius of the helical path that the proton will travel if you know that it travels 1.2 millimeter horizontal distance of its path during 2.5 times 10 to the power minus 10 seconds? So we are talking about a positively charged proton. There is a magnetic field. This charged particle is entering the magnetic field at an angle 30 degrees. This is the velocity vector, and this angle is 30 degrees. V, and this is magnetic field vector B. The equation for orbital radius r equals m y component of velocity over q times b. Mass of the proton m is 1.67 times 10 to the power minus 27 kilograms. Proton is moving, so proton is the charged particle. Q equals 1.6 times 10 to the power minus 19 coulomb. Magnetic field B is 0.65 Tesla. It's a uniform magnetic field. What about the velocity? We need to find the velocity Vy. It's a helical path, and the horizontal distance is given. This distance is d, that is 1.2 millimeter, which is equal to 1.2 times 10 to the power minus 3 meters. and time taken to cover this distance, t equals 2.5 times 10 to the power minus 10 seconds. So we can find the x component of the velocity. This is the horizontal distance, right? So if you divide horizontal distance by time taken, velocity is distance by time, you'll get the horizontal velocity d by t. So 1.2 times 10 to the power minus 3 over 2.5 times 10 to the power minus 10. 4.8 times 10 to the power 6 meter per second. X component of the velocity, 4.8 times 10 to the power 6 meter per second. We have the angle theta equals 30 degrees, and we are going to find the y component. Right? So I'll draw this vector v. So this is the velocity vector v, and this is the x component vx, and we know what is vx, 4.8 times 10 to the power 6 meter per second. And this angle is 30 degrees, and we need to find the y component. This is the y component, vy. Vx is v cos theta, and vy is v sin theta. So let's call this equation number 1 and this one equation number 2. Dividing equation number 2 with equation number 1. Vy over Vx is equal to v sin theta over v cos theta. You can cancel out v. Vy over Vx is equal to sin theta over cos theta is tan theta. We need to find Vy. So Vy equals Vx tan theta. Vx is 4.8 times 10 to the power 6 tan 30. 2.77 times 10 to the power of 6 meter per second. Okay, let's go back to our equation for orbital radius. R equals mvy over qb. R equals mvy over qb. Mass of proton 1.67 times 10 to the power minus 27 kilograms. Vy, we just found Vy, 2.77 times 10 to the power 6 over charge of a proton 1.6 times 10 to the power minus 19 times magnetic field 0.65. 0.04479 meter. Moving decimal place 2 times to the right, 4.4 times 10 to the power minus 2 meters, which is 4.4 centimeter.